So it's a pleasure to be here to present some of recent work we have been doing with quite a few people from different places as well. So that was together with a group of David Lucas and Chris Ballance from Oxford, as well as people from Lausanne, Zurich, Geneva, and us in Paris. So yeah, our work is available online. It's published in Nature now, and there are also two other works you might be interested to look into if you're into the mood to find out more. So what I want to talk about is secure communication, and so well, something that we are very used to in our digital age. So let's say Alice wants to send a password to a server held by Bob at a distance, and so, but she doesn't want anyone else to know about the password. So how could she do that? There are solutions to do that, and one is nice because it's like really proven to be secure, and it's called a one-time pad. It involves a key shared between Alice and Bob, and so Alice will basically encode her password into a message with the key and send the message over, and then Bob, having a copy of the key, will be able to retrieve the password. And why is this secure? Because anyone in the middle can access the public channel and get a copy of the message, but since the message was computed as an XOR with a fully random key, then M itself is fully random and contains no information on the password. So what we see is that secret key shared between two parties is a resource for secure communication. So the next question is, okay, how do we create this resource? And how can we distribute a key at a distance? So there are, again, several options for that, and maybe the easiest one is to meet with the person we want to talk later and share maybe a bunch of random numbers. But that's not very practical. I don't know if I would advise that, and it has limitations. And so what is mostly used today is what is called asymmetric cryptography. And it relies on some computational assumption on the power of the adversary. And given this assumption, then the encryption and decryption operation are performed with different keys, and in such a way that now an adversary having only access to the encryption key will have to solve a very difficult problem in order to retrieve the password from the message, hence the security. And so for this setting, we can ask, okay, well, that's fine, but who can really guarantee that a given function is a one-way function? And the answer is actually no one can, because at least for the system that I use today, we actually know a way to break this, and this is called Shor's algorithm, and this we know can factor numbers on which RSA, for instance, is based efficiently. And so those functions are actually not one way for quantum computers. And we can think about, okay, well, try to estimate really the resource that would be required to perform this algorithm on different architecture. And so those are some of the numbers that we come up. And so we are still safe for now, I guess. But when those would be available, well, at least this particular function will probably not be called one way anymore. But you could say, well, okay, but this was described before we even think about quantum computers, maybe. So what about finding a one-way trapdoor function on BQP? And there are efforts in this direction, and but the same question remains: who can then satisfy that the function is really one way? And as it turns out, the answer so far is still no one. And as an example, there is this competition at NIST who is basically here to define candidates for such functions, and they had come up to 4 finalists, if you want, candidates. And just last year, one of them was cracked, not with a quantum computer, but with a laptop. So of course, we hope the other ones will not suffer the same, but this is kind of the current situation. All right, so, well, given all of this, we can just ask, okay, is there actually even just one way to really distribute a key that can be proven to be secure? And so for this, we turn to quantum protocols. And here, the idea directly comes from quantum theory, from which we know that if two parties share a singlet state, then the outcomes, the theory predicts that the outcomes on one side of a measurement will be fully random and unpredictable by a third party. So we got security here. And at the same time, measurements on the other party, if it's chosen appropriately, it will be actually fully correlated with the first one, which means the secret is shared. So that's exactly what we mean by a key, a secret key. So that sounds good. And so we can look at, okay, what are the kind of assumptions involved in order to really obtain a key and according to this principle, and we can list them. There are 5, and so we need, well, to trust that physical theory applies to the adversary as well. We need to trust that information inside the labs remains in the labs. That's a basic assumption of cryptography to start with. And then we need to be able to choose numbers randomly, locally. And we also need to trust, if we have a computer we ask to produce, make a computation, we need to trust the computer will actually do what we want. Then we have this new assumption, which is basically the equivalent, the quantum equivalent, which is that when we have a quantum device and we want the quantum device to perform a quantum operation, then we just trust that it actually does what we want. And so we see that here there's no assumption about the computational power or any additional assumption on the adversary. And so in this sense, we can indeed obtain information theoretic security, which is nice. But one drawback somehow is that we had to add one more assumption here to deal with this protocol. And well, those protocols have been now out there for a long time, and experience has shown that actually this is the weak point almost all the time. And to understand why, maybe you can meet one time a quantum hacker like Bancal, and you just ask him or present to him your setup, and maybe one of the first questions you will ask is, okay, what do you actually trust about your quantum device? And what happens is that if he just manages to do something to make your device operate outside of this model, then this will open directly a breach of security. Right? So there are a number of attacks that have been using such principle. And so ideally, really, we would like to do quantum key distribution, but without adding any more assumptions compared to the usual. So we'd like to get rid of this assumption. And well, I mean, if we manage to do that, of course, we'll have more security than existing systems. But we could ask, is it still possible to actually obtain a key and to prove security there? And so if we do that, essentially what this means is that we will have to describe our devices as black boxes. And meaning we cannot assume what is inside there. And so what can we do with black boxes? Well, we can, for instance, perform a Bell test. And a Bell test is nice, as we heard just in the previous talk, because if you observe the right correlations, you can actually infer a posteriori properties about the quantum systems that you have been measuring. And in particular, sometimes you can even conclude that you actually the boxes have been measuring parts of a single state. And knowing this, and what was possible with QK, we have the feeling that, okay, this should be possible to do something there. And indeed, it's possible to compute what is the predictability of the outcome, say, of Alice here, when she performs a measurement, as a function of the winning probability of a non-local game, such as the CHSH game. And we see that this uncertainty increases with the winning probability, meaning that there is secrecy. So we have secrecy in Alice outcomes, and importantly, this bound here is valid for all possible realization that could happen inside the boxes. So it's always valid, it's device independent in this sense. And so from that, we see that the only ingredient that is missing is to now that we have some secrecy for Alice, to actually have Bob hold also a copy of this secret information. And for this, maybe we'll have to sacrifice some information to reveal it, for Alice to reveal it to Bob, for him to be able to reconcile his key to hers. And so we expect the key rate to have basically two contributions, one the secrecy of Alice string, and the other one being the cost of reconciliation. All right, so that's say, the ID. And so now how do we actually do that in practice? And so for this, we need a protocol, and the protocol will have a similar structure as usual QKD protocol, namely one quantum part which will create data, and a second part that will analyze this data and process it further. And so the first part will basically happen like this, is that every time a quantum state is created or prepared between distant boxes, then the labs need to be closed to forbid information to go out. And then either of two possible rounds will happen. Is either we'll decide to do a test rounds, meaning that both parties will actually choose settings to play the non-local game and record the outcomes, or they will try to make measurements with outcomes as correlated as possible in an effort to reduce the cost of error correction. And so this is repeated basically n times to accumulate data, and at the end of this, well, we will hold 4 strings of data that are here corresponding to the inputs and outputs of those boxes. And with this, then come all the classical post-processing. And so first, there'll be a basis revelation for Alice to announce what settings she used to Bob. Then error correction, where Alice will reveal some information about her outcomes to Bob in order for Bob to be able to guess what she had. But of course, she should reveal as little information as possible. Then there'll be validation, meaning that one player will be able to test what is the winning probability that occurred during the experiment. And given this, they will be able to put a bound on the security and therefore apply privacy amplification to extract the actual key from the whole set of the data. And finally, importantly, all the classical communication involved in the protocol will need to be authenticated, because otherwise that would be the easiest way to break the system, would be to do a man-in-the-middle attack. And this requires actually some initial secret key between the two parties. And so what this means is that in the end, the purpose of the protocol will not really be to distribute a key, but actually to expand the key. Because starting from an initial secret key, in the end, we want to produce one that is, say, hopefully longer than what we started with. And that will be, say, a success. All right, so now, to really do that in practice, of course, there are a number of challenges, and numerous groups have worked on those points in the past decades. And so I'll just mention quickly, from the theory side, of course, we want to prove security against general attacks. Then we also need to prove security and extract a key in presence of a finite amount of data, because that's what we will have. And as we'll see, we'll need also some state-of-the-art error correction to have a hope to actually be left with some non-zero key. And then on the experimental side, well, the challenges are high in terms of CHSH value that is needed, in terms of low error, and also in terms of the amount of data that is needed to be able to have a significant estimation of security. And also we need to isolate the systems. This is the cryptographic aspect of that. All right, so let's just have a look quickly at the theory side. And so there are different types of attack models that have been considered in literature. But as we said, somehow if we're interested in information theoretic security, what we really want is to make no assumption on the adversary, and therefore we will be interested in general attacks that are usually called covariant attacks. So that's what we want to look into. And knowing this, we can define security. And so there will be two contributions to the security analysis. One is the correctness, which is the probability that related to the probability that Alice and Bob actually have identical keys. And because they cannot communicate them, we can only assess that up to some finite probability. So there will be a parameter associated to that. And then the secrecy, which measures how indistinguishable is Alice key from a fully uniform string from the point of view of Eve. And so this is measured in terms of trace distance, and we just then define a unique security parameter based on those two. And so we saw, okay, the soundness depends on correctness secrecy. In practice, this will be taken care of by almost universal hash functions, and by a randomness extractor. We use the Trevision extractor. And this extractor takes as a parameter a lower bound on the smooth mean entropy. And so we need to compute this. And so to do that, we use the entropy accumulation theorem that allows us to really put a bound on this quantity that is valid for general attacks in this sequential scenario, and also in presence of finite data. And basically what this bound tells us is that we can hope to get this curve that we saw before, asymptotically, but there will be a finite size correction. And so depending on this prefactor V, well, we'll have already to accumulate many rounds and just to have some entropy left, right? And once we have entropy left, we still have to do the error correction. That will also be costly. And so for this, we our colleagues in Lausanne, Kirill, Ivanov, and Rüdiger Urbanke, who got the Shannon Prize this year, devised a code that basically fulfills all the requirements that are critical here. And those are, in particular, the most critical element would be to produce a syndrome allowing Bob to construct Alice string, a syndrome that is as short as possible. And this code is actually then has other benefits that maybe I'll just pass by to talk more about the experiment that is then allowed since we have all the theoretical ingredients. And so this experiment was performed in Oxford by our colleagues there, and what they have is 2 ion traps that are distant by about 2 meters, and in each trap they have strontium ions, one that they can manipulate very well, and in particular they can entangle the ion with a photon that they can couple into a fiber, and by sending a photon from each trap into a middle station where they perform Bell state measurement, they will herald by entanglement swapping the creation of entanglement between the 2 ions in the traps. And so when this occurs, each ion will be moved away from the focus of the fiber to isolate the system, and then where they will be measured according to settings that are chosen locally. And so this setup is really quite remarkable. In particular, it's pretty fast. You can run it has a repetition rate about 100 Hertz, and even if it's that fast, it can actually obtain violations and low noise that are pretty remarkable. I mean, that are just the best compared to other experiments. And this allows us now, if we compare to a final statistics analysis, to expect a key rate from about 1 million repetitions of the experiment. And so now in this, we actually run the experiment for 1.5 million rounds, and performed error correction, and checked the Bell violation that was observed, and this allowed us to guarantee that about 400,000 secret bits were indeed present in the outcomes that had been produced during the experiment. And knowing this, well, we had to then retract 300,000 bits roughly, that way divulgated by the error correction procedure. And with this, we were left with a new key of length about 95,000 bits. And since 256 bits were consumed by the protocol for authentication, for instance, then indeed we were able to produce more than what was consumed by the protocol. So here is the key that is not secret anymore. As the one of Alice and the one above, and we just use it between the 2 stations to actually encrypt an image of John Bell for the occasion. And with this, I thank you for your attention.
All right. So, any question? Yep.
Thank you very much. I think it's really nice to see that the finite key rate analysis is working for this. So for your setup, you had a relatively close distance. So how would it scale if you go to further distances?
To scale, you mean to larger distances?
Yes, yes, yes.
Yeah, so I mean that's kind of now the I guess the next steps, you know, is now that we know we can have a key, I guess all the kind of usual, you know, trends of QKD will also apply, and one of them is indeed trying to go to larger distances, and another one would be to have a higher key rate and stuff like that, right? So you mean how it will trend in terms of how far we will be able to go, or?
Yes, for example, with the setup you have,
with this setup?
Yeah, could you just put in a long fiber on a spool and then...
Yes. So here, the fibers are about in total maybe 3.5 meters. But at least the wavelength that is used, I forgot exactly, but I think it loses half of the signal every 100 meters roughly in that fiber, because it's not a telecom wavelength. And so that means that basically the cost will be mostly the repetition rate. So if we just go to 100 meter, we would expect to have, instead of 100 hertz, 50 hertz. But in terms of quality of the state produced, we don't really expect much difference. So that means that here the experiment lasted about 8 hours. So if we go to 100 meters, we'd expect to have exactly the same key in about 16 hours. And of course, you cannot go to kilometers like that, right? But at least that gives you a sense of how far you could go. It depends, basically, in the end, how much you are willing to wait.
Thank you.
Mm-hmm. Any other question? Well, if not in the middle, I have just a pour parler, sort of a little question. So of course, you said the usual trends of quantum cryptography, improving rates, improving distance. So of course, all this improving goes towards some kind of practical, quote-unquote, commercial application at some point. What do you think would be the first kind of use case for a device-independent key distribution?
Yeah, that's a good question. I mean, obviously, this is not the easiest way to produce a key, you know.
Yeah,
but it has the higher level of security, clearly. So we could imagine, well, applications where security is just at most important, and maybe, I don't know, government use or
I guess banks as well may be interested. I mean,
maybe. Yes. But, yeah.
Nobody has more technical questions to ask. All right, well, if not, we can have a kind of a longer break. So let's thank Jean-Daniel again.
Thank you.
Thank you.